Good. So final speaker of today, we're very happy to have Ryan Cullinan. He'll talk to us about the structure of higher dimensional integrable field theories. Please, Ryan.
Yeah, so thanks to the organisers. It's a great privilege to speak here and speak about some fun work I've been doing with some co-authors or collaborators, Marco, Alex, and Benoit is in the audience. I have the privilege of doing this. Oh no, they're good. I'll do this today where we have been battered with 4D Chern-Simons theory. So I'm going to run quite quickly through this. The sort of paradigm is four-dimensional Chern-Simons provides this systematic framework to describe, and I put in a homage to Richard Ward and his Ward conjecture. Many, perhaps all, 2D integral field theories, I mean, the omission being sort of the 2D KdV equation. But the sort of paradigm starts with you're starting with this action, which is given by this this four integral over some meromorphic one form, which is a meromorphic form this Riemann surface C, wedged against this Chern-Simons 3 form. We've seen this. The point I want to stress here is this omega contains poles and zeros, and these poles and zeros define a divisor on the Riemann surface. And essentially, all the divisor is a mapping where if I give you a marked point, I return you an integer that could be positive or negative, and negative ones correspond to poles, positive ones correspond to zeros, and the zeros just correspond to holomorphicity. So an example of this would be something like this. So this is the famous one we've seen today, the PCM omega. And I could write it out in a divisor language just like this. So 1 times 0, z0, which is one of those zeros, and then the other one. And you can see for the poles, we have a double pole at 0 and a double pole at infinity. So we don't just have this, though. We need another ingredient for 4D Chern-Simons theory. We need a choice of frame for our principal fiber bundle our connection is going to live on that trivializes the bundle over C. And essentially what this does is it means that we can write the Z, well, it means there exists a frame such that this Z bar component is a pure gauge. And with this is a formal gauge transformation we can do from our connections to write it like this, where this L is suggestively written L is purely has legs along the space-time direction. It'll turn out that this L will satisfy the following equation of motion in this sort of formal gauge. The first equation shows that it has meromorphic dependence on the Riemann curve, and the second one shows that it's flat along sigma. So it shows that it sort of coincides with this lattice connection. And we can go a little bit further, and if we define this, so this is really describing a 2D IFT is the point. And if we go a little bit further, we define this nice current type thing here. We can actually show that the action in this gauge is basically purely just a 2D IFT, this d omega localizing from x4, from x4, so integrating over the C down to 2 action sigma. And that's all I want to say about 4D Chern-Simons theory. And now I want to talk about some more recent things. So in the year 2024, there were some really, really nice papers by Alex, Benoit, Hank, and Lineado, or sorry, not Joaquin. And the idea is that instead of formulating 4D Chern-Simons theory as described in 2D IFTs, the idea was to go up the categorical ladder and use some two categorified notion of group called the 2 group, and its corresponding 2 algebra to describe integrable field theories in 3 dimensions. So much in the same way that in 4D Chern-Simons theory, the main protagonist of that theory was G-valued of one form, and it had sort of the gauge transformations, which you could think of as G-valued 0 forms infinitesimally. In 5D Chern-Simons theory, we actually have this crazy notion of doing 2 group or 2 algebra value differential forms. And you can define them sort of in this sort of way. So the same way we take the G and we tensor product it with the forms, we tensor product our complex or two algebra with the differential forms. And I've sort of tried to demonstrate this here. So the important thing here is that this two group is just consists of 2 groups, H of degree -1, and then you have this degree 1 mapping T star, which then takes you to degree 0 G. So this differential plays with the Dram differential, and when you totalize, you get this complex. So looking at sort of like this complex, we can sort of like, again, read off the protagonist of the theory. So in degree 1, we'll have our physical fields. So we'll have one form, which is just going to be the G0 value, sorry, the G valued one forms. But because we have because our H is degree -1, it's apparent that the total degree is going to be a 2 plus -1, so it's going to be degree 1, so it's a 2 form in H. And this whole paradigm continues, so the infinitesimal gauge transformations are going to be given by the degree 0 elements. So this is again 0 forms plus 1 forms in H. And then again, we actually, if you're looking back here, we have this little end here, and this is going to be our degree -1 elements, and these are going to form 2 gauge transformations.
But G is a Lie algebra, T also a Lie algebra, and H -1 is a Lie algebra.
Sure, yeah.
And H -1 lives inside G.
It doesn't necessarily have to. It doesn't necessarily have to. So for instance, we could have the only condition is these are 2 Lie groups, and there's this T star mapping that goes between them.
Does it preserve the Russell bracket? Sorry, the Lie bracket.
It has its own notion of Lie bracket. So it has this like a graded Lie bracket on this overall thing. So so H and H will vanish because of degree reasons. H and G will go to H, and G will go to G. So it's like, yeah, it has to preserve the grading basically. So yeah, in the sort of the theory of like two gauge theories, it's this well-known fact, and it's a pretty annoying obstacle actually. The collection of 2 gauge transformations fail to close unless this fake flatness condition is satisfied, which just basically says the connection is flat, or sorry, that you have this f of a minus t star of b is equal to 0. So it's some sort of indicting condition that these have to satisfy if you want to try and describe consistent closure of this. So luckily for us though, this condition is actually an equation of motion of the 5D2 Chern-Simons theory that I'm describing. And when we have gauge transformations that only close on shell, this means, well, we need to be passed to a derived setting essentially, so we adopt the BV formalism or the Batalin-Vilkovisky formalism. And essentially all this does is it adds in sort of ghosts and anti-ghosts and anti-fields. So you start with BRST with ghosts and physical fields, and you add in more fields. So the word derived here, sorry, it just means basically instead of working with things like rings or manifolds, we work with homological algebras of these rings over manifolds. So we have like things that are graded. And basically what this means is we start with the BRC complex, we just expand that in a consistent way, and you do this by adding anti-ghosts and anti-fields. One of the issues of BV formalism that is quite apparent is that unfortunately the framework is completely perturbative, in the sense that these finite gauge transformations that allowed us to trivialize our frame no longer exist in their finite form, and we only have access to infinitesimal gauge transformations. So this is kind of a sorry fact, because now how are we going to describe the dynamical fields of our sig models? Well, there is some respite in this sort of useful fact that I think is due to Costello and Quillian, that the BV formalism is essentially captured by the data of non-infinity algebras. So okay, we have to work incessantly, but like when we consider a BV formalism as an non-infinity algebra, we actually have a lot of tools from homological algebra that might be able to help us when it comes to describing theories in this framework. So this L-infinity algebra I've just mentioned is a bit of a gadget, and I think it's not fair to assume that anyone knows what it is, so I've just spent a little slide sort of trying to introduce it nicely. So all it is it's a Z-graded vector space. So it's just, a lot of vector spaces. And the idea is that these vector spaces actually have a few maps, such that when you feed me lots of different elements of the different vector spaces, these maps take however many and just push them down into one. And to do this consistently, they have to have degree 2 minus n. There's lots of reasons for this number, but I'll spare some details. And they have to satisfy these quadratic constraints. These quadratic constraints come about in many different ways. One nice way that I personally like is that it sort of is the right constraints if you want to package this into what's called the symmetric formulation, where you essentially have these L maps defining a co-differential on a differentially graded coalgebra. But essentially, for what we care about, these relations allow us to unpack what's really going on with these maps. So if these quadratic constraints hold, I've wrote down the first few here. So you have that L1 squared is equal to 0. That tells us that L1 is a degree 1 map that is nilpotent. Therefore, it forms a differential on this segregated vector space. So an infinity algebra has an underlying differentially graded algebra. the L1 has to play with the L2 map, and it does so like this, and it just shows that actually the L1 is a graded derivation of this L2 map. And then you might think, okay, well, with this L2 map, it might look, it has to be graded antisymmetric because this is these L's do. It has to be linear, so maybe it's a Lie bracket, and this is where sort of it gets interesting. In fact, the Jacobi identity for these L2s, which I wrote down to basically stop a lot of muddling around with formulas, this is just the Jacobi for L2, is actually not equal to 0. It's actually equal to this commutator term here, which basically says that this L3 bracket, which is the higher bracket over L2, in fact acts as a homotopy for the Jacobi identity. So the Jacobi identity is satisfied up to some notion of homotopy. Or like, if you want to take away, it's like it's nearly a Lie algebra, but like it's not quite a Lie algebra, but it's a Lie algebra up to nice relations. And basically, these are incredibly felicitous choice of gadget when you were trying to describe topological holomorphic theories in the BV formalism. And the reason why is because essentially the topological holomorphic theories sort of have an underlying description in terms of Dirac and de Rham complexes. So I'm going to try and set up what we should do for the 4D Chern-Simons theory, which should be familiar by now. So we have this Dirac de Rham complex in X4, like so. So yeah. So, but the problem is with this is very vanilla. It doesn't account for any of the things we need to do to when we have this omega appearing in the action. So this is kind of the big point. So all this omega does for us is it means that we have to have zeros and poles in our gauge field, and we want this complex to see these boundary conditions, these zeros. So the way we do this is we'll introduce what I call local boundary conditions later and singularity structures on our complex. And this is achieved by twisting our complex by line bundles that are defined by the divisor omega before. So yeah, this now gets upgraded and it gets So each node of this point here of this complex here, we have this twist by line bundles. And then the full 4D Chern-Simons theory, boundary conditions and singularity structure is given by this expanded. So you can see here it's got the de Rham differential Dirac, and it's got all the boundary conditions. So now to start talking about actions, we need to have a cyclic structure on L-infinity algebra. This is basically it's sort of like the L-infinity's answer to a killing bracket. So you have two elements of L, and it gives you back a C. And importantly, it has to be of degree -3. And this is quite like an easy thing to see because my physical fields are always in degree 1. So like if I want to write something down, my kinetic operator will be of degree 1, so it'll be like something field, kinetic operator field, that's degree 3. So this will have degree -3, the bracket, so then it will have me something in degree 0, which maps to something non-trivial in C, basically. So for our case here, we want something that takes in something from this complex here and with itself and gives me back something C, and the right action, obviously, is the following. So it's just the integral over X4, omega wedge, that. And then the action is given by this guy generically. And then, so where all these Ln brackets start appearing, and you notice how because these have degrees 2 minus n, as we add in more n's, this still has degree 2 and this has degree 1, so it's consistent. And in the 4D Chern-Simons case, where this Ln is just a differentially graded Lie algebra with the Lie bracket, we have this truncating at the L2 bracket, and our action is just exactly the 4D Chern-Simons theory action we wrote down before. Now, when we wanted to describe 2D integrable field theories from this framework, an important notion was obviously getting rid of the Riemann or the spectral parameter sort of Riemann surface. So in this perspective, it's not at all obvious if I just work with this complex, like how I would try and get to a 2D IFT from here. Luckily for us, there's a useful fact that integration over the Riemann surface is actually a homological operation. So it sort of can be modeled using sort of like homological algebra. So what we do is we take our BV complex and we pass it to its Dirac cohomology along C. And this is done using another tool called the strong deformation retract. And the idea is that you have two differentially differentially graded Lie algebras with some relation between them. So this I mapping and this P mapping are homomorphisms of the graded algebras, and then you have this degree -1 mapping called H, which is called the homotopy, and they have to satisfy some relations. And these relations are incredibly important. So in some sense, you have a bigger and a smaller space. So this is our bigger space, and this is our smaller space. So if we take our smaller space and we include and then we project, which is what the MP sort of stand for, we start off with something small, went something bigger, then went something small again. We lost no information, and this is this relation. If we go the other way around with something slightly bigger, we project and then we include, we would have lost some information because the I map has to be a homomorphism, so it can't. It has to, yeah, exactly. It has to be one to solve. So yeah, we can't gain more information essentially, and this is what this DH plus HD is doing. It's telling us, it's saying, okay, we lost information, but we actually, it's controlled. And if the two things have these things, you say the two are, yeah, a strong deformation of each other. I guess strong deformation retract. One is a strong deformation retract to the other. So that's just for a deformation retract. A strong deformation retract, you have these side conditions, just put there for completeness. And luckily for us, we can compute the cohomologies really easily using results from Riemann surfaces. So you just take out your favorite Riemann surface textbook minus Otto Forster's, and you read this, and then you know exactly what the setup should be for your strong deformation retract. So we start with our Debye complex C, twisted by some line bundle, again defined by some divisor, and you have this relationship where you have it your cohomology with 0 differential, and these I's and P's all depend on the divisors, and this H. So it's all this depends on the data of the divisor. So this is obviously one part of it, and then you need to use this strong deformation retract we have on the cohomology to try and construct a complex f of sigma. So this is going to be hopefully our 2D IFT complex, which is related to the 4D Chern-Simons complex by the same data, but modified by these tildes, which is a fact of what's called the homological perturbation lemma. So here we have these tildes, which are related to these I's and P's as follows. So notice in here that actually you have a D prime with 2 differentials. This is going to be quite important later, and the I's get modified by up to this homotopy using this homotopy, and so do the P's. So we can go ahead, take this complex, pass this cohomology, and this is the result. So if we twist our complex in such a way that the degree 1 fields vanish in cohomology, which is a very important result, sorry, a very important thing to do for 4D Chern-Simons theory, is essentially tantamount to saying that it's the same phrase as saying that your Z bar component of your gauge field is completely gauge trivial. The idea being that if it vanishes in cohomology, if we think of what G minus 1 dg looks like infinitesimally, it will just look like d epsilon, so it's exact. This is just the infinitesimal statement that it's gauge trivial on the Z bar direction. Passes cohomology, we find that we essentially, so we map to, so n is the degree of the divisor. So we get these, so Gn values, this is saying we have Gn copies of a group value field infinitesimally, and they satisfy some second order differential equation, and they get mapped into the equation of motion, which is a 2 form. So basically what this is saying is that D prime, D prime on the new complex is a linearized equation of motion for a sigma model, essentially. So this is like, you can see it has the right form of sort of a wavy type equation. So basically we found that this strong deformation retract using homological perturbation lemma indeed gives you a sigma model, at least at the linear level, but it's an important thing to also make statements about the non-linear level. At the end of the day, we're trying to solve integrability. And integrability, we're trying to say profound things about incredibly nonlinear equations, which look like they shouldn't be solvable in any sense. So how do we go beyond that to get to these nonlinear terms? And the idea is we actually use more results from homological algebra. So this is a really nice fact. I really like this. It's called the homotopy transfer theorem. So if I have some L-infinity algebra and I have a strong deformation retract between them, I can start transferring the L-infinity. So if I have some L-infinity structure on my underlying complex, I I can start using the L infinity structure on the bigger thing to put an L infinity structure on the smaller thing. So you take these L mappings and you can start using them to map to a bunch of L primes on the other space, which upgrades this from a differential graded algebra to an L infinity algebra. Yeah. So basically, what the idea is this map I taking you between the two then gets extended to a infinity quasi-isomorphism. Yeah. So this is actually done very systematically. So in our case, we had a differentially graded Lie algebra. So the most we have is an L2 bracket. And as such, these L prime n brackets can be constructed by summing over actually the rooted binary tree diagrams. So the idea is that I have an element, I map it using this I tilde, it maps with another one, the L2, it meets, you act with homotopy on it, etc., etc. And you just go around summing up all the possible diagrams. And if you resum up all the diagrams, you can find the higher these higher Ln prime. So for the case here, so where we've got the PCM, the data of omega being the PCM plus West amino, you can do this explicitly. And in this case, you find that you have two types of terms appearing, the odd and the evens. So we have these L primes, and basically the odd give us something that looks like the kinetic term, and the evens give us something that look like the West amino term. And essentially, this essentially corresponds to the perturbative expansion of the PCM plus West amino term when you allow G to be e to some of the algebraic valued field. So okay, I've talked about the 4D Chern-Chapman theory. We did things as a complex. We managed to from that using homological algebra get back the answer from regular 4D Chern-Simons theory beyond the nonlinear level. What can we say? Now we have this very robust framework. What can we say about the high-dimensional Chern-Simons theories? Well, the idea is that we will have a larger D-term L infinity algebra, where so this is obviously of degree G ball minus D, and then you have these the L1 the differential along the Lie algebra direction pushing you up. And what we're going to do is we're going to totalize this with the forms. I might have to maybe run to the punchline. You can construct these things, and yeah, so the geometric setup is as follows. You have some manifold that's parallelizable. You define some singularity structure in the same way as this is just giving poles to our physical fields, and you have to do them consistently, which is what these conditions are. Similarly, you have to impose boundary conditions, and the important one to focus on is that you have this one which imposes that the physical fields are of degree -1, so they vanish in cohomology. So you can then combine using the local boundary conditions of the singularity structure with the totalized complex from before. And I focus on a very nice example for this collection of boundary conditions in our paper. And the idea is you get this complex of for a 3D IFT, and you get essentially that the equations of motion can be captured by a sort of linear wave-like equation with a Lorentzian metric. And I'll skip the conclusions. Thank you.
Thank you, Ryan, for the talk. Any questions?
Yeah, thanks for the nice talk. So the boundary conditions and the singularities you impose by twisting the gauge fields by some line bundles, does this work for like the non-local boundary conditions you might use for, say, Yang-Baxter sigma models?
These fall out of the realm of our framework superficially, but I think Lewis has been doing some interesting work with Sylvan, and I think that there's a way of, I guess so, but if there's a way of framing these non-local boundary conditions locally, then they would form, they could be, put in this form. So I think it maybe some minor modifications, yes, if okay. So basically these non-local boundary conditions are actually Dirichlet boundary conditions in disguise.
And does this homotopy transfer technique work for obtaining 4D IFTs from twistor space?
Yeah, it has a similar story for the twistor space. Yeah.
Thank you.
For the 60, yeah.
Hi, could you say again how, give some intuition for how passing to this L infinity model allows you to take into account non-perturbative?
Okay, so the way the non-perturbative stuff happened was essentially by calculating. So a priori, there's no way I could say without doing the computation this always happens, right? Like, you know, it's like something that. So this is not like I say a resolution to BV not working perturbatively. This is not like a non-perturbative description of BV. All this is saying is that if I work with the tools that perturbative BV give me, calculate the higher brackets, resum them, I get exactly what I would have got with using the frame field in the first place, basically. It's quite a nice, it's like a really nice, well, it's a very satisfying result.
Yeah, thank you for the nice talk. I think it's probably related question, but so in particular, when you have the Wessamino term, and it's not a very precise question, so I apologize but
No.
But in particular, when you have the Wessamino term, when you expand in terms of algebra valued fields so that you can write it locally in 2D, you lose some information about the global. In particular, this model will not have a G times G symmetry anymore. Do you see any way of kind of restoring that or kind of going back to writing this in terms of G? I mean, it always feels more natural to write this model in terms of G. Here, you naturally get it in terms of phi. Do you see any way of kind of getting back to G?
I mean, the way is, I mean, this is the issue is that you have to be smart and know the answer, right? Like you can say like, okay, well, I know that this resums to the PCM when I let this happen. So like, I guess like, the idea is that if you take the PCM, you expand it like this, you get this answer. So when you find this answer, you know. So I mean, yeah, there's no way a priori. I don't know of a way where I can say, oh, okay, generically, how are we going to get the full group valued field out? Because the BV formalism just doesn't use finite
gauge. This is related to this point that that there is no that the BV formula is inherently perturbative.
Yeah, exactly. Inherently perturbative. Like, it doesn't know how to deal with finite gauge transformations.
Okay, thank you.